Welcome to the second video of the last section, Throttling Messages Pattern. In the previous video, we saw how to balance our workload across nodes. We also discussed how to implement Balancing Dispatcher with remote actors. In this video, we will take a look at another pattern called Throttling Messages. We will take a quick overview on this pattern and then take a look at the implementation, and finally, we will use this pattern. Let's start. Sometimes in our application, we need to make HTTP requests to an external web service, and this service has some limitations. If we exceed the specific number of requests in a specific period, we will get a block or a need to pay. So, you need to make sure your application doesn't exceed this limitation. With the throttling message pattern, we will make sure the messages are not sent out at a high rate. The throttler will be based on a timer. This means, at every interval, the throttler will send a specific number of messages. For example, if you want to send 3 messages every second, the throttler will receive messages from you and will send exactly 3 messages each second. And if it receives more than 3 messages per second, it will enqueue them and send them in the next interval. Now, let's take a look at the pattern skeleton. Here is a skeleton of the time-based throttler. It is an FSM actor that has 2 states, idle and active. The data will contain the target actor, number of messages that got left in this period, and the queue of messages. Throttler will take a rate of messages on the constructor. It will start on the idle state with data that contains target as none. A number of left messages on this period will be a rate, and an empty queue. On the transaction from idle to active, we will set a timer, and from active to idle, we will cancel the timer. This timer will send a tick message at every duration from the rate. In the idle state, it will handle set rate, set target, and enqueue any other messages. When a set target message arrives and our queue is non-empty, we can start sending messages. When a set target message arrives and our queue is empty, we stay, recording the new target. When a queue message arrives and the target is not set, we stay in idle, after adding the new message to our queue. When a queue message arrives and the target is set, we jump to active, delivering the message that we just received. In the active state, it will handle set rate and set target like in the idle state. When a set target message arrives to unset the target, we jump to idle. With no target given, all we can do is queue messages. When a set target message arrives to change the target to another one, we update our internal state, D. When a queue message arrives and we have vouchers left, we use them. When we've run out of vouchers, we put the message at the end of our queue. Now, let's implement a simple example that uses throttling actor messages. This pattern is on the External Contributions subproject on Akka, and the recommended way to use something from this module is by copying the source code on your own code base and changing the package name. Because the Akka team does not restrict updates to this subproject, even during the otherwise binary compatible releases, and modules may be removed without deprecation warning. So, I just copied the timer-based throttler to our project. And now, let's define a simple actor. First, let's start to define our actor that receives messages from timer-based throttler. It's a simple actor. When it receives anything, it will print a message with the current time. Now, let's define our throttler instance. We will create props of timer-based throttler and our rate will be 3 messages per second. Now, let's send our target to throttle, and, then, let's send 5 messages. Let's run. If you noticed, the first 3 messages are received in the first second, and the last 2 messages in the next second. We discussed the throttling message pattern in this video, and how to implement it. You can check full documentation from here. See you in the next video on shutdown patterns.